Hey guys, welcome back. This is going to be lesson 4.4, transformations of linear functions. This is supposed to be a 2-day video, but I'm going to cover it in one shot. For the goals here, we're going to apply translations to linear functions, apply dilations to linear functions, and apply reflections to linear functions. I recommend you pause the video and go ahead and write down these vocabularies into your foldable. Real quickly here, family of graphs or any graph or equation that have at least one characteristic in common. A parent function is just the simplest of that function family. So if we have y equals x, we can write that as f of x equals x, and then f of x equals x becomes our parent function. An identity function, that's just another name for a parent function. A transformation here is any kind of movement of the graph which can create a new linear function. What we're about to do today actually applies to all the different functions we'll be dealing with, not just linear. A translation is the most basic. That is a sliding of the graph, and the key here is without being turned. You can slide it up, down, right, or left. A dilation is a stretch or a compression of the graph for linear functions. Basically what that means is that the graph will get steeper or it gets flatter. And the last part here is a reflection, and that's simply a flipping of the graph across a line, and that line will either be the x-axis or the y-axis depending on the reflection type. And what I mean by that is either vertical or horizontal. Okay, so here are the first three examples. One vertical translation, one horizontal, and then a multiple of both horizontal and vertical at the same time. I'm going to show you real quickly on here what it looks like, and then I'm going to go over to Desmos to show you exactly what the translation or transformation would look like. So the first thing you want to notice about vertical translation is the translation occurs outside the function. And when it happens vertically, that means the calculation is happening directly on the y value. So if I had a point somewhere that was, let's say, 2, 5, in order to apply this transformation to it, this minus 2 here is actually only going to affect the 5. So the translated point would be 2, comma, and then 5 minus 2, which of course would be 2, comma 3. So the point 2,5 would translate into the new point 2,3, doing a vertical translation. When we get to horizontal translations, this is really tough for students. Remember, it's actually going to be the opposite of what we always have, because this plus right here was actually a minus, which means we must have input a -5. So we're not really adding 5 to our x value, we're subtracting. And keep in mind, horizontal translations are going to affect the x value only. So let's go back to that other point where I had 2,5 was the original problem. And then I apply this translation of, it says +5, but remember it's really minus a -5, so I'm really subtracting 5. So the translated point is going to be 2 minus 5, comma, and then the 5 here doesn't change. So if I adjust that, 2 minus 5 will give me a -3, 5. Okay, so something I want to point out is when we did the vertical translation, the x value stayed the same before and after. When I did a horizontal translation, the y value stayed the same before and after. The only thing that changed was the x and y's, depending on if it was vertical, up and down, which is a change in the y, or horizontal, left and right, which is a change in the x. For this last one, where we want to do multiple translations, I'm going to go back to that original point again of 2,5, and I'm going to do a translation on it. This translation right here is really going to be +6. So that's going to give me a new ordered pair of 2 plus 6, comma. This is the x value. And then this +3 here is affecting the y, which is going to give me 5 plus 3, which is the y coordinate. And the final translated point would be 8, comma 8. So this point here translates to 8, 8 on the graph. So when you have multiple translations, you're changing both the x and the y from beginning to end. All right, so here we are in Desmos, and I'm going to put in y equals x. You can see that makes the parent function of a linear. I'm also going to put in f of x equals x and show that that's actually the same function. So I'm going to get rid of the original equation form. I'm just going to go by function form, which is f of x. And we're going to do a horizontal change. So if we go back to our example we had, x minus 2. So that's going to be g. So I'm going to put in g of x, and that's going to equal f of x minus 2. That's the same thing as coming up and putting a minus 2 right here next to the x. And what you'll notice is, let's say I put in a point 2, comma 2. You'll notice that this point right here was just shifted down 2 units. Okay, 2, comma 2, that's the same thing as leaving the first 2 alone, and then taking the output and subtracting 2 from it. Because remember, this is a vertical translation, so we're minusing 2 from this. And we end up with this point right here, which is 2, 0, 2 units directly below. So that's just 2 units down. So minus 2. If I go look at the other one, the horizontal translation was plus 5. Now remember, this is always the opposite, so it was like it was taking away 5 from the x. So this point right here should move 5 units to the left. So 1, 2, 3, 4, 5 units to the left. So that point should appear over here. So I'm going to give it a different name though. I'm not going to call it G. I'm going to call it H. So H of x is going to equal the same f of x as before. But instead of minus 2 on the outside, I'm going to put plus 5 on the inside. So plus 5. Let me change the color here. So the first 2 that was right here, I subtract 5 from it, and now I get a 2 that's over here, or a coordinate over here, which is actually 5 units to the left at negative 3, but the y coordinate is still the same. If I go and do this calculation, I'm going to do a plus 6 and a plus 3 to it. I'm going to give that another name also, so I'm not going to use the same variable. So we'll call this j, function j. So j of x is going to equal f of x. And then I'm going to put my plus 6 in there. I think it was plus 6. Nope, it's minus 6. So we're going to put minus 6 inside. So it's going to move the graph 6 units to the right. Okay, so it moved it 6 units to the right. But then I got to put my plus 3 on the outside. So plus 3, it's going to move it up 3 units. So plus 3. So this point right here moved 6 units to the right. I think I'm going to go off the graph a little bit. Let me move this over. This x moves 6 units to the right. So that should be at 2 plus 6, comma. And this one's going to move 3 units up. That would be 2 plus 3. And if we look at the ordered pair there, you'll notice that this point here translated to that point over there through both calculations. Okay, for examples 5 and 6, we're going to talk about dilations. Now, the first thing you want to know about dilations is vertical dilations and horizontal dilations in linear functions are the same as long as the parent function is being used to transform. So if I put a times 2 like this on the outside of my function versus the inside of my function, like that, so that would be, let's say, g of x times 2 here versus g of 2x. Okay, so this is outside, that's vertical. Inside, this is horizontal. The effect in both of these is to make the graph steeper. So if we look at it on a graph, it's going to look like it's exactly the same calculation or the same transformation. The only difference is when it's on the outside like this, we call it a vertical dilation. And anytime it's bigger than 2, this number, remember this is a times g of x. Anytime the a value is bigger than 1, a is bigger than 1, we call it a vertical stretch. And if a is bigger than 0 but less than 1, in other words, some sort of decimal or fractional value, then we call it a vertical compress. And these two things right here you might want to write down in your foldable. And what this is telling us right here, whether I have it written like that or I have it written like this, is, remember, g of x is the output values. It's telling us that all the output values, also known as the y values, are going to get 2 times bigger, which is what creates the steeper look to the line. Now compare that to horizontal dilations. Down here we have the same scenario where the multiplication here is either multiplied by a number bigger than 1 or smaller than 1 but greater than 0, but its interpretation is different. When it's horizontal, meaning it's inside, when A is greater than 1, it's called a horizontal compress. And when A is bigger than 0 but less than 1, it's called a horizontal stretch. This 1/4 x really means I'm making my x values 4 times bigger. So this transformation would actually be opposite of what you're thinking. It's not really divide by 4, it's really 4 times 4, comma 6, which would give us 16/6. Okay, so here we are in Desmos. We've got our parent function again, or our identity function, if that's what you want to call it. And I'm going to do a multiply here. So let's go with g of x, and let's say g of x is equal to f of x. So in other words, they're exactly the same line right now. But let's suppose I take g of x and tell it to be equal to 2 times the f. So put it times 2 out in front, and you see that the graph becomes steeper because all the output values became twice as big. If I look at this point right here, which is 2, 2, this formula over here says to multiply the output, which is this one, by 2. So my new order pair would be 2, 4. So 2, 4 you can see is right there, and that's how it translates. If I look at the next one over, this one right here, which is 3, 3, 3, 3, and I'm supposed to multiply the output value by 2, I end up with 3, 6. So if I go over 3, 6, you'll see the outputs right there. Now if I were to do the same thing with times 2 on the inside, I'm going to change my function now. H of x is going to equal not times 2 on the outside, but times 2 on the inside. I'm going to change my color. You'll notice if I turn this on and off, the lines look the same, but what's happening here is the interpretation of what's happened is different. Okay, so this is no longer called a vertical stretch. Now when we compare that to the bottom function here, this is horizontal, and I know it's horizontal because the calculation occurs inside on the x. What's happening is all of my x values are getting 2 times smaller, not 2 times bigger. So in that context, we are compressing this thing horizontally, which means we're pushing inwards from the outside like this, and the graph is still going to move in this direction. So to give you an idea of what's going on here, so let's suppose I look at this point right here, which is 4, 4, and then I do a horizontal compress of a factor of 2. It means I'm going to take my 4 value, which is here, and divide it by 2. So 4 divided by 2 is 2. And now if I go over to 2, 4, you see that point translated over here. So the reality is, when we look at a straight line or linear function based off the parent function, a vertical stretch and a horizontal compress look exactly the same. For our last two examples, 7 and 8, we're talking about reflections. So we got a reflection across the x-axis, and that's because it was a vertical reflection happening outside like that. And the other one is across the y-axis, and that's because it was a horizontal reflection happening inside like that. Now the thing that they did here was, instead of putting just a negative, they included these numbers with the negative signs. They shouldn't have done that, because what they've done is they've combined a stretch and a compress with a reflection. They should have just done the reflection. Now we're going to run into the same problems we did before. If we base our transformation off of the parent function, a horizontal reflection and a vertical reflection are going to look identical. So another way of writing this would be negative 1/2 g of x. The same scenario down here for reflection across the y-axis. So this right here could be the same as g of negative 3x. Okay, so here we are back at Desmos. And let's say we take function g, and let's do function g as a reflection over the x. So that means you're going to change the y value. You can do a vertical reflection. So g of x is going to equal f of x. And if I put a times negative on the outside, you'll notice how it flips around like this. All right, so I'm going to leave that one there, but I'm going to turn it off. Then I'm going to go to function h and let h of x equal f of x. So that looks like the parent function, but now I'm going to put a negative on the inside. And you'll see that it looks a whole lot like the one underneath it.